Have you ever stopped to wonder what the most fascinating truth about black holes really is? The kind of truth that sounds impossible at first, yet turns out to be beautifully real. What if some of the calmest, most dreamlike ideas in the universe are hidden inside the darkest objects we know? Tonight, we are not here to be overwhelmed by space. We are here to gently explore it, one thought at a time. Welcome to Facts for Sleep. This video is an invitation to slow down. As the night settles in, we will travel together through a sequence of intriguing and soothing facts about black holes. Carefully connected, so your mind can simply drift from one idea to the next. You do not need to remember everything. You do not need to analyze or solve anything. These facts are here to spark quiet wonder, then softly fade into the background as your body relaxes and your breathing becomes slower and deeper. As you listen, a gentle 432 Hz background tone will flow beneath the narration. Think of it like a soft hum of the universe itself, steady and comforting, never demanding your attention. Let it blend with the words, creating a calm rhythm that makes it easier to let go of the day. If your thoughts wander, that is perfectly fine. If your eyes close, that is even better. This video is designed to meet you wherever you are in this moment. Tonight, you will hear about black holes, not as threats, but as cosmic mysteries filled with strange beauty. You will imagine light bending, time stretching, and space behaving in ways that feel almost like a dream. Each fact gently opens the door to the next, forming a smooth path rather than a series of sharp turns. Whether you stay awake for the whole journey or drift off halfway through, the experience will continue to carry you forward. Before we begin, take a moment to get comfortable. Adjust your position. Let your shoulders relax. Unclench your jaw. Take one slow breath in and let it out without effort. There is nothing you need to do right now except listen. And if this is your first time here at Facts for Sleep, I invite you to subscribe to the channel. Your support helps this quiet space grow and reach others who need calm, curiosity, and rest at the end of their day. If relaxing facts and peaceful storytelling help you unwind, this channel was made for you. Thank you for being here. Thank you for choosing curiosity and calm tonight. Now, let the sound soften, let the universe open gently, and let's begin. A black hole is not a giant cosmic vacuum cleaner that sucks up everything nearby. If the sun were magically replaced by a black hole with the same mass, Earth would keep orbiting almost the same way. What changes is not the pull from far away, but what happens extremely close to the object. The real drama begins near a boundary called the event horizon, where escape becomes impossible. To understand why that boundary is so strange, we need to talk about what the event horizon actually means. The event horizon is not a solid surface, even though people often picture it like a dark shell. It is more like a one-way border in space and time, where every possible path forward leads deeper in. Light can still travel there, but it cannot travel outward once it crosses. For a distant observer, something falling in can appear to slow down and fade as its light struggles to climb out. This raises a wild question. If time seems to behave differently near the horizon, what happens to time itself near a black hole? Near a black hole, time can run at a different pace compared with faraway space. The closer you are to the black hole, the more extreme the difference can become. In a sense, gravity is not just a force, it also shapes how clocks tick. This means two people could experience very different amounts of time and still reunite later. Once time starts stretching like that, the next thing to ask is what happens to space and to your body as you fall. If you fell toward a black hole, gravity would pull harder on your feet than on your head once you got close enough. That difference is called tidal force, and it can stretch objects into long strands. People nickname this spaghettification because the stretching can become extreme. The details depend on the black hole's mass, because bigger black holes can have gentler tides near the horizon. That leads naturally to a bigger mystery. How can some black holes be so massive that whole solar systems could fit inside their horizons? There are black holes with masses millions or even billions of times the mass of the Sun. These are called supermassive black holes, and many galaxies appear to host one at the center. They likely grew through a mix of feeding on gas and merging with other black holes. Their gravity helps shape the motion of stars near a galactic core, like an unseen conductor. Once you know galaxies can have central black holes, it becomes irresistible to wonder whether our own galaxy has one too. The Milky Way appears to have a supermassive black hole at its heart, known as Sagittarius A star. We cannot see it directly, but we can track stars that orbit an invisible mass in a tiny region of space. Those stars move so fast and along such tight paths that only something extremely massive and compact makes sense. It is like watching leaves swirl around a drain you cannot see, yet the swirl reveals the drain. If we can infer a black hole by the motion of stars, the next question is how we can ever actually see one. Even though black holes are dark, the space around them can glow intensely. Gas falling in forms a spinning disk that heats up through friction and compression. That disk can shine brighter than entire galaxies in some cases. The black hole itself stays hidden, but the hot matter around it tells a story in light. And if matter can glow near the edge, the next step is to ask whether we can capture the silhouette of the edge itself. Scientists have managed to image the shadow of a black hole by observing how it bends light around it. The shadow is not the horizon, but the dark region created when light paths are captured or redirected. This required linking radio telescopes across Earth so they act like a planet-sized instrument. The result looks like a glowing ring with a darker center, a kind of cosmic donut. That ring hints at an even stranger effect. Black holes can act like extreme lenses that warp the background universe. A black hole's gravity can bend light so strongly that it creates distorted images of stars and gas behind it. In some setups, the light can loop around the black hole one or more times before reaching you. This means the black hole can produce multiple images of the same object, stacked like ghost copies. If you could hover safely, the sky would look twisted and repeated in mesmerizing ways. Once we accept that black holes bend light, the next surprise is that they also can launch brilliant jets that look like the opposite of swallowing. Some black holes power enormous jets that blast matter outward at near light speed. These jets come from the surrounding disk and magnetic fields, not from inside the black hole. The system can convert a fraction of the infalling matter into focused beams that extend far beyond the galaxy. It is one of the universe's most dramatic examples of turning gravity into light and motion. If black holes can both swallow and power jets, we should ask what happens when two black holes meet and merge. When black holes orbit each other, they can lose energy in the form of ripples in space-time. As they spiral inward, they speed up until they finally collide and become one larger black hole. The merger releases an enormous burst of gravitational waves that can pass through Earth without damaging it. Instruments can detect these waves as tiny changes in distance, smaller than an atom's width. Those waves open a new kind of astronomy, which leads to the next question. What else can gravitational waves tell us about black holes we cannot see? Gravitational waves let us hear black holes that are otherwise completely dark. They reveal the masses of the black holes, how fast they were spinning, and how far away the merger likely occurred. Sometimes the masses are larger than what we expected from typical stars, hinting at unusual origins. Each detection is like a new chapter about how black holes are born and grow. That brings us to the most basic puzzle of all. Where do ordinary black holes come from in the first place? Many black holes form when a very massive star runs out of fuel and collapses under its own gravity. If the core becomes dense enough, nothing can stop the collapse, not even the pressure from atoms. The outer layers may explode as a supernova, while the core continues inward. What remains can be a neutron star or a black hole, depending on the mass. Once you know black holes can be born from stars, the next mystery is how small a black hole can be. A black hole can be surprisingly small in physical size compared with its mass. The boundary size depends on mass, and for a stellar mass black hole, it can be only tens of kilometers across. That means you could pack several suns worth of mass into a region the size of a city. This extreme compactness is why the gravity near it becomes so intense. With something so compact, it is natural to ask what, if anything, sits at the center. At the center of a classical black hole lies what physics calls a singularity, a point where density and curvature blow up in the equations. Many physicists think this is a sign that our current theories are incomplete, not that nature truly makes infinite values. It is a bit like a map that breaks down at the edge of a known region. The singularity is hidden behind the horizon, so we cannot directly check it with telescopes. That secrecy sets up the next big riddle. If we cannot see inside, can information ever truly be lost? Black holes created a famous debate about whether information disappears forever. If you throw in a book, the black hole seems to erase the details, leaving only mass, spin, and electric charge visible to the outside. This clashes with a principle in quantum physics that information should not be destroyed. The tension between these ideas is called the black hole information problem. And to deepen the mystery, black holes might not even be perfectly black. According to quantum theory, black holes can slowly emit a faint glow, now called Hawking radiation. This radiation comes from quantum effects near the horizon, not from anything escaping from inside. Over extremely long times, this would cause a black hole to lose mass and eventually evaporate. For most black holes, the effect is far too weak to measure with today's technology. But if black holes can evaporate, we must ask what happens to everything they swallowed as they fade away. If a black hole evaporates completely, the information question becomes sharper. Does the outgoing radiation somehow encode what fell in, or is it random noise? Different ideas propose that information is subtly stored on the horizon, or that the radiation carries hidden patterns. The deeper answer likely requires a better theory that unites gravity with quantum physics. Each proposal sounds like science fiction, yet it comes from real math. And while theorists debate, observers ask a more grounded question. How do we know a black hole is there if it emits no light? One common method is to watch a normal star orbiting an invisible partner. If the star moves as if tugged by a massive object you cannot see, that invisible object becomes a candidate black hole. In some systems, gas pulled from the star falls toward the unseen companion and heats up, producing bright radiation. This makes the system visible, even if the black hole itself stays dark. These paired systems are like cosmic detective stories. Following that thread leads to another striking fact. Black holes can spin, and spin changes everything. A spinning black hole drags space around with it, a phenomenon called frame dragging. Near the black hole, this effect can be so strong that objects are forced to rotate in the same direction. The spin also affects how close matter can orbit safely before plunging in. Faster spin can allow the inner edge of the disk to sit closer, which can increase heating and brightness. Spin can also help power jets through magnetic effects. If spin reshapes the neighborhood, the next question is what the closest stable orbit looks like. There is a region around a black hole where orbits become unstable. If you go too close, a tiny nudge can send you inward across the horizon. The boundary depends on the black hole's mass and spin, so it is not a one-size-fits-all rule. This is why the inner disk has a sharp inner edge in many models. It is also why falling in can become inevitable once you cross a certain line. That inevitability brings up a curious idea. Could there be a place outside the horizon where you cannot stand still? Around a spinning black hole, there is a zone called the ergosphere, where space itself is dragged so strongly that standing still is impossible. You could still escape from this zone if you fire a rocket, but you cannot hover without rotating. In theory, you can extract energy from a spinning black hole using processes that exploit this dragged space. It is like tapping the rotational energy of a cosmic flywheel. This makes black holes not only destroyers, but also potential engines. Once we talk about extracting energy, it is natural to wonder how black holes influence entire galaxies. When a supermassive black hole feeds, it can release tremendous energy into its surroundings. That energy can heat gas, blow winds, and sometimes slow down star formation in the host galaxy. In other cases, shocks and pressure can compress gas and help trigger starbirth in certain regions. So the black hole can shape the life cycle of a galaxy, even though it occupies a tiny central volume. It is a small object with a huge reach. And if black holes affect galaxies, we should look at the most extreme feeding events of all. Sometimes, a star wanders too close to a supermassive black hole and gets torn apart by tidal forces. The shredded material forms a temporary disk and can flare brilliantly. These are called tidal disruption events, and they let astronomers watch black holes suddenly light up. For a short time, the galactic center can become a beacon as the star's matter spirals inward. It is a dramatic reminder that gravity can be both beautiful and brutal. This naturally raises the next question. Can black holes ever wander away from galactic centers? Black holes can be kicked around by gravitational interactions. When two black holes merge, the gravitational waves can carry away momentum in uneven directions, giving the new black hole a recoil. In principle, this could shove it off-center, and in rare cases, even eject it from the galaxy if the kick is strong enough. Smaller black holes can also drift through galaxies as relics of old stellar deaths. A roaming black hole would be hard to spot unless it feeds. That brings us to a more everyday curiosity. Could a black hole ever be close to our solar system? There is no evidence that a dangerous black hole is lurking near Earth. And if one were close, we would likely notice its gravitational effects on planets and comets. A black hole with the mass of a star would pull on the solar system in obvious ways. A much smaller black hole could be stealthier, but it would still be constrained by many observations. The universe is vast, yet our local neighborhood seems calm. Still, the thought experiment is fascinating because it forces us to ask what would happen if you try to approach one safely. And that leads to the question of whether any spacecraft could ever visit a black hole. Visiting a black hole up close is less about surviving the pull and more about surviving the environment. The area around an actively feeding black hole can be filled with intense radiation and high-energy particles. Even before you reach extreme gravity, the disk can cook anything that gets too close. A quiet black hole with little surrounding gas would be less deadly in that way, but navigation and communication would become complicated. Gravity would distort signals and timing in ways that challenge engineering. Once you imagine a visit, the next idea is even more mind-bending. Could a black hole be used as a shortcut through space? Some mathematical solutions in physics describe wormholes, which are like tunnels connecting distant regions of space. People often connect wormholes with black holes, since both involve extreme curvature. However, there is no evidence that real, stable wormholes exist in nature. Many models suggest they would collapse or require exotic forms of matter that we have not observed. Still, the concept is compelling because it shows how flexible space-time can be in theory. And if space-time can be that flexible, the next question is whether black holes might have formed in the very early universe. It is possible in some theories that tiny black holes could have formed soon after the universe began, from dense fluctuations in matter. These are often called primordial black holes, and they are a candidate for certain cosmic mysteries. If they exist, they could range from very small to very large, depending on how they formed. Detecting them is challenging, so scientists look for subtle gravitational signatures rather than light. This idea connects black holes to the origin story of the cosmos itself. And that takes us to a final mind stretch. Black holes may be some of the clearest places where our best theories collide. Black holes sit at the crossroads of gravity, quantum physics, and the nature of reality. They force us to confront questions about time, information, and what it means for something to be observable. Every new observation, from star orbits to gravitational waves, adds another clue, but also sparks deeper puzzles. In a way, black holes are not just objects in space, they are laboratories for the limits of human understanding. The more we learn, the more the universe feels like a story with hidden chapters. Black holes do not have hair, in the sense that, from far away, they seem shockingly simple. No matter what you throw in, a black hole is described externally by just mass, spin, and electric charge. That means a mountain of messy details gets hidden from the outside view. This simplicity is so extreme that it feels like nature is playing a magic trick with complexity. It is one reason black holes feel like the ultimate cosmic compressor of reality. And once you accept this strange simplicity, the next question is whether black holes can be weighed from light alone. Astronomers can estimate a black hole's mass by watching the glow of gas as it orbits. Faster orbit speeds usually mean stronger gravity and therefore a more massive black hole. The temperature and brightness of the disk also depend on how close the gas can circle safely. By modeling these patterns, scientists can infer the mass even without seeing the black hole directly. It is like hearing an engine and guessing the size of the machine from the sound. Once we can weigh them, we naturally want to compare them, and that leads to black holes of different sizes in the cosmic family. Stellar mass black holes are typically a few to a few dozen times the mass of the Sun. They form from the collapse of massive stars and are scattered throughout galaxies like invisible fossils. Intermediate mass black holes, if confirmed in large numbers, would sit between stellar and supermassive ones. Their existence matters because they could be the missing stepping stones for building the giants in galactic centers. Finding them is hard because they are quieter and rarer. That hunt sets up the next curiosity. How do you even search for something that mostly stays dark? One way to find hidden black holes is to look for their effect on nearby stars in crowded places. In star clusters, an unseen heavy object can subtly change the motions of many stars over time. Another method is to catch a brief flash when a black hole pulls material from a companion star. Sometimes, astronomers also look for tiny distortions in starlight as a black hole passes in front, bending light by gravity. Each method is a different sense, like touch, hearing, and sight, used to detect the invisible. And once we talk about bending starlight, we arrive at an eerie idea. A black hole can make a ring of light. If a black hole lines up just right with a distant star behind it, gravity can focus the star's light into a bright circle. This is a gravitational lensing effect, and the ring is sometimes called an Einstein ring. In reality, the ring might be incomplete or warped, depending on alignment and motion. The black hole acts like a lens with no glass, shaping light through gravity alone. The ring is not a halo around the black hole. It is a distorted picture of something far behind it. That illusion invites a deeper thought. Black holes can distort not just images, but also what near and far mean. Near a black hole, the concept of distance becomes slippery because space itself is curved. Paths that look straight far away can curve inward near the black hole. Light rays that would have traveled freely instead bend and can even loop. This can make the region feel like a funhouse mirror for geometry, except the mirror is space-time itself. The closer you get, the more extreme the bending becomes. And once geometry becomes that strange, the next question is what an observer would actually see while falling. If you fell toward a black hole, the view of the universe could become increasingly distorted into a bright, warped patch overhead. Light from behind you might curve around and appear in front of you, depending on the path. In some scenarios, You could even see multiple images of the same star in different places. The black hole would not just be a dark circle, it would be the center of a swirling visual storm. This is one reason black holes are so popular in imagination, because they would look truly alien. And after we picture the view, we have to confront the feeling. Would you notice the moment you cross the horizon? For a very large black hole, crossing the event horizon might feel surprisingly ordinary at first. There is no alarm bell, no sudden wall, and locally, physics can seem normal for a while. The key is that the horizon is a boundary defined globally by escape routes, not a physical object you bump into. The danger comes later, as tidal forces eventually grow and the path inward becomes unavoidable. This nothing special here moment is one of the most unsettling facts about horizons. It sets up the next mystery. If the crossing can feel normal, why do some theories suggest the horizon could be violent? Some ideas in theoretical physics propose that the horizon might not be a smooth, calm boundary in every situation. There have been debates about whether quantum effects could create a kind of energetic barrier in certain models. Other approaches insist that a falling observer should experience nothing unusual at the horizon, at least for large black holes. The disagreement shows we are still stitching together gravity and quantum rules. Black holes are where those stitches are tested the hardest. That tension leads naturally to a related puzzle. Where does the entropy of a black hole come from? A black hole has entropy, which is a measure of how many hidden internal arrangements could correspond to what we see from outside. Strangely, the entropy scales with the area of the horizon, not the volume inside. This suggests the horizon acts like a storage surface for information in some sense. It is one of the most famous clues that reality might behave like a kind of hologram, where a surface encodes a deeper interior. Even if that idea feels abstract, the area rule is a real, powerful result in physics. And once entropy enters the story, the next question is how hot a black hole can be. Hawking radiation implies black holes have a temperature. Smaller black holes are hotter, while larger black holes are colder. A supermassive black hole is extremely cold compared with everyday objects, which is why its radiation is so faint. A tiny black hole, however, would radiate more intensely and evaporate faster. This flip in behavior is counterintuitive because we usually expect bigger things to hold heat better, not be colder by nature. The temperature story makes evaporation feel more real, which leads to a stunning thought. The end of a black hole could be an explosive finale for the smallest ones. As a small black hole loses mass through radiation, it gets hotter, which makes it radiate even faster. This can create a runaway effect near the end of its life. In some models, the final stage could release a burst of high-energy radiation. We have not observed such an event, so it remains a theoretical possibility rather than a confirmed cosmic firework. Still, it shows black holes are not always eternal. They can have life cycles. And thinking about life cycles leads to an even stranger question. Could a black hole be created by humans? Creating a black hole in a laboratory would require concentrating enormous energy into an unbelievably tiny region. Our current technology is nowhere near that, and even the most powerful particle accelerators are far from the needed conditions. Some speculative theories involving extra dimensions suggested tiny black holes could appear at high energies, but there is no evidence that has happened. The practical answer is that black holes are not something we can manufacture in any realistic way today. Yet the thought experiment is useful because it highlights just how extreme black holes are. And once we mention accelerators, a common fear appears, which deserves a clear fact. Particle accelerators are not going to destroy Earth with a black hole. Cosmic rays hit Earth's atmosphere at energies beyond what our accelerators produce, and the planet is still here. If tiny black holes could form at those energies, they would either evaporate instantly or pass through without growing dangerously. Nature has run this experiment for billions of years, so black holes remain cosmic phenomena, not a lab accident risk. With fear addressed, we can return to wonder and ask how black holes can be so efficient at turning matter into energy. Matter falling toward a black hole can release an enormous fraction of its energy before crossing the horizon. The energy comes out as heat and light from the disk, powered by gravity and friction. In some cases, this can be more efficient than nuclear fusion in stars. That is why active black holes can shine so brightly across the universe. It is not the black hole glowing, it is the work done by gravity on the infalling matter. And when brightness becomes extreme, we meet the most famous lighthouses powered by black holes. Quasars are among the brightest objects in the universe, and they are fueled by supermassive black holes devouring gas. Some quasars outshine their entire host galaxies. We see them from very far away, meaning we are looking back in time at an early universe full of intense feeding. The existence of very early quasars suggests some black holes grew rapidly, faster than simple growth models might predict. This makes quasars not just bright, but also deeply puzzling. And that puzzle points to a new question. How did the first supermassive black holes grow so fast? To build a supermassive black hole early in cosmic history, you need either a heavy seed or unusually fast feeding, or both. Some models propose direct collapse of giant gas clouds that skip normal star formation. Others suggest repeated mergers of smaller black holes in dense early environments. There may also be episodes of near maximum feeding, where the black hole grows at the fastest rate nature allows. The fact that we see big black holes so early tells us the universe learned to make giants quickly. And if growth can be that fast, the next question is what limits growth? There is a natural limit to how fast a black hole can feed while shining, because the outgoing radiation can push gas away. When the surrounding light becomes intense enough, it acts like a wind that fights further inflow. This creates a kind of balance point that can regulate growth. Yet black holes sometimes seem to grow anyway, suggesting clever pathways like feeding through thick flows or chaotic streams. Growth is a tug of war between gravity pulling in and light pushing out. That tug of war sets up another curiosity. Can black holes ever starve and go quiet? Many supermassive black holes are quiet for long periods, barely eating at all. They sit in the center of their galaxies like sleeping giants, exerting gravity but not producing brilliant light. Feeding depends on whether gas is delivered to the center, which can be triggered by galaxy collisions, instabilities, or chance clouds drifting inward. This means black hole activity can turn on and off across cosmic time. Our own central black hole is relatively quiet today, which is why the Milky Way looks peaceful. A sleeping giant still has effects, and that leads to the question of how black holes influence star orbits over millions of years. Stars near a black hole can have their orbits reshaped by gravitational encounters with other stars and compact objects. Some can be flung inward, some thrown outward, and some end up on wild, elongated paths. In extreme cases, a black hole can slingshot a star to such high speed that it escapes the galaxy entirely. These hypervelocity stars are like cosmic cannonballs fired by gravity. Their existence shows black holes can act as celestial accelerators. And once we talk about acceleration, the next step is to ask whether black holes can also accelerate particles to unbelievable energies. The regions around feeding black holes can be factories for high-energy particles. Shocks in jets and turbulent magnetic fields can whip particles to extreme speeds. These particles can then produce high-energy light like X-rays and gamma rays when they collide or spiral. This is one reason black holes are tied to some of the most energetic phenomena we see. They are not just about darkness, they are about extreme light and motion. And this naturally points to the question of how astronomers see black holes using different kinds of light. Astronomers study black holes across the electromagnetic spectrum, from radio waves to gamma rays. Radio can reveal jets and the structures near the horizon in some cases. Infrared and visible light can track stars orbiting an unseen mass. X-rays often come from the hottest inner parts of the disk, where gravity is strongest. Each band is like a different camera filter, showing a different part of the story. And with all these tools, the next thing to ask is how we can map the environment closest to a black hole without going there. One technique is to watch how the brightness flickers over time. The fastest flickers often come from the smallest regions, because light cannot vary faster than it can travel across the source. If the brightness changes in minutes, the emitting zone must be compact on that scale. This lets astronomers estimate how close the emission is to the black hole. In a way, the black hole's neighborhood reveals its size through its rhythm. Those rhythms lead to another fascinating detail. Some black holes show repeating beats called quasi-periodic oscillations. Quasi-periodic oscillations are patterns in the X-ray brightness that repeat with a rough regularity. They likely arise from matter orbiting and wobbling in the inner disk, where gravity is extreme. The exact cause can involve disk vibrations, hotspots, or changes in flow geometry. These beats can hint at the black hole's mass and spin, because orbital timing depends on gravity. It is like hearing a drum pattern and inferring the size of the drum. And once we mention spin again, we should explore a surprising fact. Spin might decide how close you can orbit before falling. For a rapidly spinning black hole, the innermost stable orbit can move closer to the horizon compared with a non-spinning one. Closer orbits mean higher speeds and higher temperatures, which changes the disk's light. This can also affect how efficiently the system converts infalling matter into radiation. In other words, spin can dial the brightness knob of an active black hole. It is another way black holes behave like engines, not just pits. And this raises the next question. Can we measure spin from far away? Spin can be inferred by studying the shape of certain spectral lines in X-rays that are distorted by gravity and motion. As light climbs out and as the disk matter moves fast, the lines smear and shift. The closer the inner disk extends, the stronger these distortions become, and that depends on spin. Scientists also use models of disk brightness and polarization to estimate spin. It is not like reading a label, it is like solving a puzzle from clues in the light. Once we talk about polarization, we reach a cool fact. Magnetic fields near black holes can be mapped in a visual way. Polarized light can reveal the direction and structure of magnetic fields around a black hole. By measuring how light waves are oriented, astronomers can infer how magnetism threads the disk and the region near the horizon. This matters because magnetic fields can channel energy into jets and control how matter spirals inward. It is like seeing invisible lines that shape the flow of plasma. When you can map magnetism, you can better understand why some black holes are jet monsters, while others are quiet. That leads to the next fact. Not all black holes are equally good at making jets. Some black holes launch powerful jets, while others with similar mass barely produce any. The difference may depend on spin, magnetic field strength, and how the gas falls in. A disk that is thick and magnetically choked might create conditions that favor strong jets. The orientation of the disk and the history of feeding events can also matter. This means two black holes can look totally different, even if they share the same mass. And if appearance depends on environment, the next question is how black holes behave when their feeding supply changes suddenly. When the inflow changes, black holes can switch modes of activity. In smaller systems, like black holes in binary pairs, the disk can transition between states that are brighter or dimmer in different kinds of light. These changes can happen over days to months, which is fast on cosmic scales. The behavior is tied to how hot, thick, and turbulent the disk becomes. It is like watching a storm system reorganize itself. This quick variability suggests black holes can be studied like dynamic characters, which leads to the next fact. We can learn from smaller black holes to understand bigger ones. Stellar mass black holes and supermassive black holes obey many of the same physical rules, just scaled up. The same kinds of disks, jets, and magnetic processes appear across a vast range of masses. The main difference is the timescale, because bigger systems evolve more slowly. By studying fast-changing small systems, astronomers can test ideas that would take centuries to watch in galactic centers. It is like using a model organism in biology, but cosmic. And that scaling idea takes us to another curiosity. Black holes can be described in surprisingly universal formulas. Many black hole properties follow clean relationships, such as how horizon size grows linearly with mass. Orbital speeds and characteristic timescales near the black hole also scale in predictable ways. This is why black holes feel like simple atoms in gravity, with behavior determined mostly by a few parameters. Yet the physics around them can still be messy because the surrounding gas is turbulent and complex. The contrast between simple core and chaotic environment is part of their charm. And that contrast points to a powerful observational trick: measuring black hole mass by reverberation. Reverberation mapping uses time delays between changes in the bright central source and echoes in surrounding gas. When the inner region brightens, more distant gas clouds respond slightly later as the light reaches them. The delay tells you the size of the region, and the gas motion tells you the gravity, letting you estimate the black hole mass. It is like shouting in a cave and timing the echo, but on a galactic scale. This technique helps weigh black holes in active galaxies too far away to track individual stars. And once we can weigh many black holes, we can ask how they relate to their host galaxies. There is evidence that the mass of a galaxy's central black hole correlates with properties of the galaxy's central bulge. This suggests black holes and galaxies grow in a connected way. Feedback from active black holes may regulate gas and star formation, shaping the bulge over time. Meanwhile, the galaxy supplies the gas that helps the black hole grow. It is a long dance of mutual influence rather than one side dominating completely. This connection hints that black holes are not just passengers in galaxies, they are part of the architecture. And if they shape architecture, we should look at how galaxy collisions change the story. When galaxies merge, their central black holes may eventually find each other and form a binary pair. As the galaxy's stars and gas settle, the black holes sink toward the shared center through gravitational interactions. Over time, the pair can tighten its orbit until gravitational waves take over and finish the job. This is one of the main pathways to growing supermassive black holes. It also means the universe may be full of black hole binaries at different stages. That naturally leads to the question of whether we can spot a binary supermassive black hole before it merges. Astronomers search for binary supermassive black holes by looking for unusual patterns in light and motion. Some active galaxies show periodic brightening that could hint at two black holes disturbing the disk. Others show double sets of emission features that might suggest two centers of activity. Direct imaging of two close supermassive black holes is extremely difficult because the separation is tiny at great distances. Still, evidence is accumulating in clever, indirect ways. And once we talk about pairs, we reach a truly cinematic idea. A black hole can ring after a merger. After two black holes merge, the new black hole is not instantly calm. It can vibrate, releasing gravitational waves in a fading pattern called a ring-down. The frequencies of that ring-down depend on the mass and spin of the final black hole. Measuring those frequencies is like striking a bell and identifying its shape from the sound. This offers a way to test whether the object is really a black hole, as predicted by Einstein's theory. If the ring matches the prediction, it strengthens the case for general relativity. And that brings us to an even broader fact. Black holes are among the strongest tests of Einstein's gravity. Einstein's general relativity predicts how space-time curves and how black holes should behave. Observations of star orbits, black hole shadows, and gravitational waves have repeatedly matched those predictions. But scientists keep looking for tiny deviations, because even a small mismatch could hint at new physics. Black holes are so extreme that any new rule of nature might reveal itself there first. In that sense, black holes are like stress tests for the universe's operating system. And if we are stress testing gravity, we should mention a subtle point. Even light can be trapped in orbit near a black hole. There exists a region where photons can orbit a black hole, called the photon sphere in simple models. These orbits are unstable, meaning a slight push sends the photon either outward to escape or inward to be captured. The photon sphere contributes to the bright ring appearance in black hole images, because light can skim around the black hole before leaving. It is a place where the idea of orbiting light becomes more than a metaphor. This is one of the strangest consequences of curved space-time. And once light can orbit, we can ask a very human question. What would it mean to fall forever? From your own perspective, you would reach the horizon and pass it in a finite amount of time. But to a distant observer watching your light signals, you might appear to slow, dim, and never quite cross, because signals get increasingly red and delayed. This creates the feeling of two different stories depending on viewpoint. Both descriptions can be consistent because space-time slices reality in different ways for different observers. It is not just a trick, it is a deep feature of relativity. That split viewpoint leads to the next puzzle. Where does the you end up in the black hole information story? If information is preserved, then in principle, the story of what you were might be encoded in subtle correlations in the radiation or on the horizon. Some ideas suggest the horizon acts like a ledger that records everything that fell in. Other ideas restructure the notion of interior and exterior so that contradictions disappear. None of these concepts are fully settled, but they show how black holes push physics into philosophical territory. They force scientists to ask what inside even means. And speaking of inside, we can explore another mind-bender. The interior of a black hole might not resemble the simple picture of a point in the middle. In many models, the interior is not like a room with a center you can reach and stop at. It is more like a direction in time that points inevitably toward the singularity. Once you cross the horizon, moving toward the center can be as unavoidable as moving into the future. This flips the usual intuition of navigation because the forward direction becomes inward. It is one reason black holes feel like traps in the structure of time, not just space. And if the inside is time, like in that sense, it invites the next question. Can anything ever come back out in any form? Classically, nothing that crosses the horizon can return. But quantum physics complicates the picture by allowing radiation to emerge and by raising questions about how boundaries store information. Still, no signal from inside can be sent outward in the usual sense. This preserves the black hole's role as a one-way boundary in general relativity. The only escape we talk about is indirect, through quantum effects and evaporation over immense times. That makes black holes feel like the universe's ultimate locked room. And locked rooms make us curious about what happens if you try to throw something incredibly dense in, like another star. A black hole can swallow a star, but it might not do so all at once. Tidal forces can strip the star, pulling streams of gas that wrap around like ribbons. Some of that gas may be flung away, and some may settle into a disk that feeds the black hole. The process can generate a flare that lasts months or years, letting astronomers watch the feast. It is less like gulping and more like shredding and spiraling. This eating process highlights how important tidal forces are, which leads to a subtle fact. Tides depend strongly on the black hole's mass. For smaller black holes, tidal forces near the horizon are stronger, so objects get torn apart earlier. For supermassive black holes, the horizon can be so large that a star could cross it before being fully shredded, depending on details. This means the danger zone is not simply the horizon, it can be outside it for smaller black holes. It also means tidal disruption events are most common in a certain range of black hole masses. The universe has preferred conditions for visible shredding. And once we talk about what gets shredded, we should ask about what gets compressed. Can a black hole compress matter beyond imagination? The densities involved in forming a black hole are so extreme that our usual picture of matter breaks down. Atoms cannot remain intact, and even the structure of nuclei becomes irrelevant compared to gravity. In that regime, we do not have a fully complete understanding of what matter is in the deepest sense. Black holes, therefore, hide a frontier of physics about ultimate compression. They are not just objects, they are questions wrapped in gravity. And this naturally leads to another frontier, the boundary between neutron stars and black holes. Neutron stars are incredibly dense objects, supported by the pressure of tightly packed neutrons. But there is a limit to how massive a neutron star can be before it collapses into a black hole. The exact value depends on the uncertain physics of ultra-dense matter. Observations of massive neutron stars help narrow the possibilities, but the edge remains an active research area. This makes the neutron star to black hole boundary one of the universe's great threshold lines. And thresholds bring us to another dramatic event. When two neutron stars merge, they may create a black hole. When neutron stars collide, they can briefly form a hypermassive object that is unstable. It may collapse into a black hole in milliseconds or seconds, depending on conditions. The merger can also produce a burst of gravitational waves and a brilliant explosion called a kilonova, powered by the creation of heavy elements. In some cases, a short gamma-ray burst can be launched, likely involving a newly formed black hole and a disk. These events connect black holes to the origin of gold and other heavy elements in the universe. And from there, the next question is, how black holes participate in the cosmic chemical story over billions of years. Black holes do not directly create elements like stars do, but they can influence where and when star formation happens. By heating or stirring gas, they can change the rate at which new stars are born, which changes how elements are produced and distributed. Jets can also push material far from the center, affecting the galaxy's gas cycle. In this way, black holes can indirectly shape the chemical evolution of galaxies. They are like regulators of the cosmic kitchen, even if they do not cook the elements themselves. This brings us to a more personal curiosity. Why do black holes capture our imagination more than most other objects? Black holes combine simplicity and mystery in a way humans find irresistible. They are predicted by elegant equations, yet they hide regions we cannot observe directly. They warp time, bend light, and challenge our common sense. They also connect to deep questions about reality, like whether information can be lost and what space-time truly is. In storytelling terms, black holes are the perfect mix of monster and mirror. And since they are so iconic, it is worth exploring one more subtle truth. Black holes are not isolated. They can have weather. The environment around a feeding black hole can be turbulent, like a cosmic storm. Magnetic fields twist, plasma whips around, and hotspots flare and fade. The disk can have waves, eddies, and sudden reconnection events where magnetic lines snap and rejoin, releasing energy. This creates variability that astronomers monitor like meteorologists tracking patterns. The black hole's neighborhood can be dynamic, even when the black hole itself is simple. That weather idea naturally leads to the next question. Could there be seasons in black hole activity across a galaxy's life? Over billions of years, a galaxy can go through phases where its central black hole is highly active and phases where it is quiet. Mergers can deliver gas and trigger a bright active phase, while calm times lead to starvation. The black hole's feedback can then alter the galaxy, influencing how much gas remains to feed it later. This creates a long cycle of cause and effect that can repeat in different ways. It is a slow cosmic drama with episodes and pauses. And if galaxies have black hole seasons, it is natural to ask what the universe looked like during its most active era. The early universe appears to have hosted many more bright, active black holes than we see nearby today. Quasars were more common, meaning supermassive black holes were feeding aggressively. This suggests galaxies had more central gas available or more frequent disruptions. It also means black holes have been shaping galaxies since very early times. Looking at distant quasars is like watching the universe in its energetic youth. That time travel perspective leads to another mind stretch. Black holes help us study cosmic history by acting as beacons. Because quasars are so bright, we can see them from vast distances. Their light passes through gas clouds and galaxies along the way, imprinting subtle fingerprints. By analyzing those fingerprints, astronomers can map the distribution of gas in the universe over time. In this sense, black hole-powered quasars illuminate the cosmic web like flashlights shining through fog. They do not just tell us about black holes, they reveal the universe between us and them. And once we talk about using black holes as tools, we reach a surprising idea. Black holes could be used as natural telescopes. In theory, a black hole's gravitational lensing could magnify distant objects behind it. The alignment would have to be just right, but gravity can bend and focus light in powerful ways. This could boost the brightness of otherwise faint galaxies or stars, making them easier to detect. Nature sometimes provides this lensing for free, and astronomers take advantage of it. It is a cosmic magnifying glass with no glass at all. And if black holes can magnify, it invites an even weirder possibility. Could they also hide things by bending light away? Extreme gravity can redirect light so that some regions behind a black hole appear dimmer or distorted. Depending on geometry, a black hole could act like a lens that both brightens some angles and darkens others. This is not invisibility in a magical sense, but a real optical effect of curved paths. It shows how black holes can reshape what is visible in their neighborhood. Even the act of looking becomes complicated near them. That complexity leads to the next question. What does it mean for a black hole to have a shadow at all? A black hole's shadow is really a map of which light paths are lost and which survive. It depends on where the glowing material is and how the light travels through curved space-time. The shadow can change in appearance if the black hole spins or if the disk's structure changes. In that way, the shadow is a dynamic portrait, not a static emblem. Watching the shadow over time can reveal turbulence and motion near the horizon. And this invites another thrilling idea. Could we make a movie of a black hole changing? With repeated observations, it is possible to reconstruct time variation in the bright ring region around some black holes. Instead of a single snapshot, astronomers can look for changes in brightness patterns that shift as plasma swirls. This is like taking blurred frames of a storm and combining them into a sequence. The timescales differ by mass, so supermassive black holes evolve slowly compared with small ones. Still, even slow changes can be measured with patience and technique. And once we talk about time series, we reach a key fact. Black holes can be used to test whether light speed is truly constant in extreme gravity. General relativity assumes light travels at the same speed locally, but gravity changes how light paths appear when measured from far away. By comparing signals and timing near black holes, scientists can test models of curved space-time. Different kinds of emission can originate at different radii, giving natural timing experiments. While we are far from placing a stopwatch at the horizon, we can still compare delays and distortions. Each comparison is another attempt to see if nature matches our equations. And if we are comparing signals, we should mention that black holes are also powerful sources of neutrinos and cosmic rays in some scenarios. Some black hole systems may produce high-energy neutrinos through particle collisions in jets or surrounding regions. Neutrinos are ghostly particles that rarely interact with matter, so they can travel vast distances without being stopped. Detecting them can point back to violent cosmic accelerators. This is a different window into black hole environments, one that does not rely on light alone. When neutrinos join the story, black hole astronomy becomes multi-messenger. And multi-messenger astronomy leads to the next idea. Combining gravitational waves with light gives a fuller picture. When a compact object merger produces both gravitational waves and a light signal, we can learn far more than from either alone. The waves tell us the masses and dynamics, while the light reveals the environment and element creation. This joint view can confirm whether a black hole formed, how much material remained outside, and what kind of jet emerged. It is like hearing the thunder and seeing the lightning from the same storm. Multi-messenger events are among the most exciting frontiers in astronomy today. And as we hit the frontier, we should bring up a beautifully simple question. Why are black holes black? A black hole is black because light cannot escape from within the horizon. Even if light is produced inside, every path forward leads inward rather than outward. From outside, we only see what happens in the surrounding region, not the interior. This is different from a dark object like a planet, which can reflect light. The black hole's darkness is not about color. It is about causal structure, about what can influence what. That causal structure is one of the deepest ideas in physics, and it leads to another. Black holes divide the universe into regions that can and cannot communicate. The horizon marks a boundary of communication, not just motion. Events inside cannot send signals to the outside, meaning the outside universe can never be directly updated by what happens beyond that border. This makes horizons feel like cosmic censorship, hiding the most extreme outcomes of collapse. Whether this censorship is always guaranteed is still a topic of debate in certain theoretical scenarios. But in all known realistic astrophysical cases, horizons appear to do their job. And once we talk about censorship, we should explore an even more mysterious concept. Can a horizon be replaced by something else? Some speculative ideas propose alternatives to traditional black holes, such as ultra-compact objects without a true horizon. These could mimic black holes closely while differing in subtle ways, like echoes in gravitational wave signals. Such ideas are studied because they might resolve certain paradoxes, though they are not confirmed by evidence. Most current observations are consistent with ordinary black holes, as described by general relativity. Still, scientists keep testing because the stakes are enormous for fundamental physics. That relentless testing brings us to a down-to-earth question. What is the closest confirmed black hole to us? Astronomers have identified black hole candidates relatively nearby in our galaxy, often in binary systems. The distances are measured in thousands of light years, which is close by cosmic standards, but still unimaginably far for travel. These nearby systems are important because we can study them in detail and watch them change in human timescales. They teach us about feeding, jets, and variability up close. Each nearby black hole is like a local laboratory for extreme physics. And from laboratories, it is natural to ask, what would a black hole sound like if you could translate its signals into audio? Scientists sometimes convert black hole-related data into sound, a process called sonification. Changes in brightness, orbital frequencies, or gravitational wave signals can be mapped to audible tones. This helps people recognize patterns and can make complex data more intuitive. Gravitational wave chirps, in particular, naturally translate into a rising tone as two objects spiral together faster and faster. Hearing it can make the event feel real in a visceral way. And once we are listening to black holes, we should ask whether they can also be felt through their effect on space-time. Gravitational waves are literally tiny stretch and squeeze patterns in space-time itself. When they pass through Earth, they alter distances by an incredibly small amount. Sensitive detectors can measure this, turning space into a kind of instrument. It is astonishing because it means black holes can influence us without light, across billions of light years. The universe has multiple languages for communication, and gravitational waves are one of the newest we have learned to understand. This new language opens the door to detecting mergers that produce no light at all. And that takes us to an eerie thought. Most black hole events may be happening in total darkness. Many black hole mergers likely occur in regions with little gas, so they produce almost no light. Without gravitational wave detectors, we would never know they happened. This implies the universe is full of silent collisions, shaping black hole populations over time. The sky we see in light is only part of the universe's story, like hearing only the loudest moments of a long conversation. Gravitational wave astronomy fills in the missing chapters. And once we talk about populations, the next question is how many black holes might exist in a typical galaxy. A galaxy like the Milky Way likely contains many stellar mass black holes created over its lifetime. Most would be isolated and therefore hard to detect because they do not shine unless they interact with matter. They would drift through the galaxy as dark remnants of long-dead massive stars. Their presence would be felt mainly through rare interactions or subtle gravitational effects. The idea that we live in a galaxy full of invisible, heavy objects is both spooky and awe-inspiring. That atmosphere sets up the next curiosity. Could black holes contribute to the universe's missing mass problem? Dark matter is an unseen substance inferred from gravity, and black holes have been considered as a possible contributor in some models. Primordial black holes are one candidate that might account for a fraction of dark matter if they exist in certain mass ranges. Observations place strong limits, so it is unlikely that black holes make up all dark matter, but the question is still actively explored. This is a perfect example of black holes reaching into cosmology, not just stellar death. It reminds us that black holes sit at the center of many mysteries at once. And that brings us to a final, satisfying truth that ties the journey together. Black holes are simultaneously simple objects and bottomless questions. They can be defined by a few numbers, yet they force us to rethink time, space, heat, information, and the limits of observation. They power the brightest beacons, generate invisible waves, and shape galaxies across billions of years. They are reminders that the universe can be both mathematically elegant and emotionally overwhelming. If you started this journey thinking of black holes as just dark holes in space, you end it seeing them as gateways into the deepest laws of nature. And the best part is that every new discovery suggests there is still another surprising fact waiting just beyond the next horizon. As we reach the end of this little voyage, past glowing rings and quiet horizons, let everything slow down. Imagine the black hole not as something frightening, but as a gentle reminder that the universe is wide, patient, and full of secrets we do not need to solve tonight. Let your thoughts drift like starlight, soft and weightless, until they fade into the calm dark of your own sky. Breathe in, breathe out, and allow the noise of the day to fall away, one small worry at a time. May you sink into a deep, comfortable sleep, and may your dreams be entirely yours, warm, vivid, and safe, carrying you to places only you can see. And if the cosmos whispers anything as you rest, let it be this simple promise: tomorrow there will always be another horizon to explore.